All right, today we grapple with some more rotational quantities here. I always like to start with an analogy because we've done a lot of work in this class that could help us. When I think about rotational quantities, I first think about, well, what I know about linear quantities, and then I think about the analogies to rotational quantities. Okay? So, in linear quantities, we thought about the linear momentum. Well, it's a vector, it points, okay? And the analogy in rotational quantities is the angular momentum. So linear momentum and angular momentum. And further, we know that our linear momentum is m times v, where this is the mass and this is the velocity. Well, there's a similar analogy in rotational motion. That is, I don't have the mass, I have something called the moment of inertia. Okay, multiplied by omega, which is our angular velocity. So, just like mass, sort of the inertia, or provides inertia for our objects, it's a resistance to changes in velocity. Moment of inertia is the same thing. It's resistances to changes in angular momentum. So it has to do with the distribution of mass, not the total mass itself. And we'll talk about this some more. Okay? So I want you to focus in this chapter, or in this reading, on the examples. They're really good, okay? When you think about, I want you to have a clear idea about how we connect torque, how we connect moment of inertia and angular velocity and angular momentum. So if you're struggling with these concepts, certainly come and chat with me, but I just wanted to make one thing clear, okay? We've put a lot of these pieces together already. I have a demo for you that I hope might help, okay? So I have this wheel on a frictionless bearing, okay? So I'm going to do a couple of things to this, right? First thing that I'm going to do is I'm going to apply a force tangential to get this thing spinning. That is, I'm applying a torque from this force, okay? Now, when I apply this force, I get the thing spinning. But I want you to remember that the torque I produce is in this direction because it's R cross F. So we use the right-hand rule. So if I apply a force like this, I exert a torque in that direction. So force gives me a torque in this direction. R cross F gives me a direction of torque that's along the axis. Now, when I do that, I produce an angular acceleration that's also in that direction. Okay? So I'm speeding up I'm increasing the angular speed because the torque and the angular acceleration point in the same direction. So I'm speeding up the angular speed. Finally, once I do that, once I get this thing spinning like this, it has an angular momentum. The angular momentum in this case is going to point upward. So if it's spinning around like this, the angular momentum points in the direction of the angular velocity, which is in this case kind of up. Do the stop and think problem, 9.5. It's a really good one. But if you want to play with this demo, it might be a really good idea, particularly if you're having a hard time conceptualizing the direction of these vectors because it's very tricky. Okay? Take your time, do good work in this, and ask yourself tough questions.